Assalamualaikum warahmatullahi taala wabarakatuh. Very good day to everyone. Alright, so basically, we have discussed on the first law of thermodynamics in previous video. So today we focus on the second law of thermodynamics. Okay, so we have three parts, and this is the part one. We discuss on the heat engine. The introduction about heat engine. Okay, second law of thermodynamics. In the first law of thermodynamics, provide the basic definition of internal energy, and it associates with all thermodynamic system and states the rules of conservation of energy. So the second law is concerned with the direction of natural process. It asserts that a natural process runs only in one sense and is not reversible. For example, heat always flows spontaneously from hotter to colder place and never the reverse unless external work is performed on the system. So its modern definition is in terms of entropy. So this is the general equation for entropy. So entropy is your change in heat divided by temperature. Thus, we can summarize that the second law of thermodynamics as the entropy of an isolated system not in equilibrium will tend to increase over time, approaching a maximum value at equilibrium. So basically it's a one way. So process occurs in a certain direction and not in the reverse direction. So one way process. So the process is something like this is must flow for the first law. So in actual thermodynamic process, a process must satisfy both of the first and second law of thermodynamics to proceed. In other words, all process is obeying the first law and the second law. The second law of thermodynamics, major use of the second law. The second law may be used to identify the direction of the process. So the second law also asserts that energy has quality as well as a quantity. The first law is concerned with the quantity of energy and transformation of energy from one form to another with no regards to its equality. The second law provides the necessary means to determine the quality as well as the degree of degradation of energy during a process. The second law of thermodynamics is also used in determining the theoretical limits for the performance of commonly used engineering systems such as heat engine and refrigerator, as well as predicting the degree of completion of chemical reaction. So this is the example of second law. So for first figures, a cup of hot coffee does not get hotter in a cooler room. So basically, the hot coffee will reduce the amount of heat whereby the heat will be released to its surrounding, and by time the hot coffee will get warm, and by time to time it will be colder. So this is the sample of materials. Figure 2, table 2, figure the material that has a specific energy, which is, for example, uranium. They have very high specific energy, up to 80 millions, okay, megajoules. And the lower is wood, which is about 16.2 megajoules. Okay. So basically this is the material for a combustion. And this is the example of combustion. Thermal energy reservoir. In the development of second law of thermodynamics, it is very convenient to have a hypothetical of thermal energy reservoir or just a reservoir. Thermal energy reservoir. A body with a relatively large thermal energy capacity or mass times specific heat that can supply or absorb finite amount of heat during undergoing any significant change in temperature. So that we call it as a thermal energy reservoir. We have two types of thermal energy reservoir. First, we call it as a source. Second is the sink. So, for a source is a supply finite amount of heat without undergoing any change in temperature. The sink absorb finite amount of heat without undergoing any change in temperature. So, in practice, a large body such as sun, ocean, lakes and river as well as atmospheric air can be modeled accurately as thermal energy reservoir because of their large thermal energy storage capabilities or thermal mass. So something like this. This is your source, sun. So basically, this is your sink. So the source will supply the heat. The sink will absorb the heat. So this is the example of reservoir. Heat engine. The thermal energy reservoir or just reservoir can simply be modeled as heat engine. What is heat engine? Heat engine employs a range of methods to apply the heat and to convert the pressure and volume change into a mechanical motion. For example, convert heat to work. Heat engine involve four processes to convert heat into work. So the first is they receive heat from high temperature source. For example, solar energy, furnace or nuclear reactor. And number two, they convert part of this heat into a work, usually in the form of rotating shaft. And number three, they reject the remaining waste heat to a low temperature sink. For example, atmosphere, river, and other adsorbent material. And number four, the last is they operate on a cycle. So heat engine and other cyclic device usually involve a fluid to and from which heat is transferred while undergoing a cycle. So this fluid we call it as a working fluid. So this is the example of heat engine. So we have a high temperature, the source, and we have a sink, a much more lower temperature. So in the middle we have a heat engine. So heat being supplied Q in. So this is a Q out. Maybe we can derive as a heat loss. And this is the network output. So example of everyday heat engine includes the steam engine. So for example, most of the world's power plant use steam turbine and modern form of steam engine and the internal combustion of engine, gasoline, which is a petrol engine, and the diesel engine in a automobile or truck. The work producing device that best fit into the definition of heat engine is the steam power plant, which is an external combustion engine. So this is the example of heat engine. We have a boiler, so a pump, a condenser, and a turbine, which is the boiler receive heat, our source such as a furnace that supply the heat, and the working fluid. This is your working fluid. We move the turbine, that turbine producing power, and the hotter fluid will be cooled in a condenser and then pumped back to the boiler. So the net work is work out minus work in. So in this example, we have work out from the turbine minus the work pump. Also, in work out, work net is on the Q in supply minus Q out. So that is also a work out, work net. Thermal efficiency. Based on the cycle of the steam power plant and the third major use of the second law of thermodynamics, the magnitude of the energy used in order to complete the cycle or the performance of the power plant can be measured. This measurement called thermal efficiency, and mathematically we can calculate as the efficiency is your desired output divided by your required input. So normally we need a output is a work divided by your heat input. So the net work output, work net divided by work in. So from work net is your Q in minus Q out, heat in minus heat out. So we can rearrange, substitute work net into this equation. So we have Q in minus Q out divided by Q in. And then we can cancel out. We have efficiency, thermal efficiency, 1 minus Q out divided by Q in. So same with this, 1 minus QL over QH. So this is the example. Okay, as we assume that Q in is your higher side, we change Q in with Q hotter plate, hotter. So QL is your Q lower. So it's the same methodology we use in this area into this area. So Kelvin Planck statement. Kelvin Planck statement states that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. No heat engine can have a thermal efficiency of 100%, or as for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. So that is the third major use of second law of thermodynamics. So basically the impossibility of having a 100% efficient engine is not due to friction or other dissipate effect. It is a limitation that applies to both the idealized and actual heat engine. So in actual, the efficiency may not exceeding 100%. So a heat engine that violates the Kelvin Planck statement or second law, which is no heat waste. So which means that if you have a thermal energy reservoir producing 100 kilowatt of heat supplied to the heat engine, so the work output, work net is 100 kilowatt, no heat loss. So basically this is a heat engine that violates the Kelvin Planck statement. Sample problem.
Sample problem 4.1. A steam power plant produces 50 megawatts of net work while burning fuel to produce 150 megawatt of heat energy at the high temperature. Determine the thermal efficiency of the cycle, and B, the heat rejected by the cycle to the surrounding. Alright, so 4.1. Okay, so basically here we have steam power plant produce net work. Given directly, work net 50 megawatt, while burning fuel at Q high is 150 megawatt. Okay, so refresh back, your work net is Q high minus Q low. Okay, so basically here, thermal efficiency, the efficiency of the system is work net. So this is the desired output divided by QH. This is your input. Okay, is equivalent to 1 minus Q low per Q high. Okay, so the efficiency, we use this equation because we have all. So basically we have 50 megawatt per 150 megawatt. So we have 0.3 times 100%, we got 30%. Okay, all right. Heat rejected, B, heat rejected, Q low, being rejected to the surrounding. So work net is equal to Q high minus Q low. So Q low, Q high minus work net. So we have Q high 150 megawatt minus work net 50 megawatt, 100 megawatt. Alright, thank you.
4.1 Sample problem 4.2
Sample problem 4.2. Heat is transferred to a heat engine from a furnace at a rate of 80 megawatt. If the rate of waste heat rejection to a nearby river is 50 megawatt, so determine the net power output and the thermal efficiency for this heat engine. So 4.2. So we have the source. Okay, so basically this is your QH, this is your engine producing watt, so this is your work net. Okay, and this is heat being surrounded, rejected to a here is a river, so Q low, rejected. So work net is not mentioned, so basically the heat transfer to furnace is 80 megawatt, Q low is 50 megawatt. So that is this in the given directly from the question. So A, net power output, work net. So basically work net is equal to Q high minus Q low So 80 megawatt minus 50 megawatt. So we got 30 megawatt. The efficiency. So the efficiency is 1 minus low minus QH is equivalent to 1 minus 50 megawatt per 80 megawatt. So punch out your calculator, you got your answer. Okay, thank you.
Sample problem 4.3.
Sample problem 4.3. A car engine with a power output of 65 horsepower has a thermal efficiency of 24%. Determine the fuel consumption rate of this car if the fuel has a heating value of 44,000 kilojoule per kg, which is that is 44,000 kilojoule of energy is released for each kg of fuel burn. Alright, so basically here we have 4.3. Okay, so work net, the power output, work net is 65 horsepower. The efficiency given is 24%. Okay, the heating value, HP calorific value, 44,000 kilojoule per kg. So we need to change this first using kilowatt units. So work net 65 HP times 0.7457 kilowatt HP, 1 HP. So you can calculate, you got kilowatt. Okay, all right. And then for the heat supply QH is work net per efficiency. This is in general equation. So we have kilowatt 0.24. This is percentage. This is not in percentage. Okay, so we got the value kilowatt, unitless kilowatt. Okay, all right. So M fuel is equals to kilowatt. What is kg per second? So we have your value kilowatt or kg, kilojoule per second, divided by 44,000 kilojoule per kg. Okay, so we using kilojoule per second, so this is time out, so kg per second. So your unit is kg per second. That is your flow rate. So what is your calculate the value lah. So here, put in here, you got your value. Okay, all right, thank you.